My name is Nathan Eubens. I'm a PhD student at the University of Mons in Belgium and Polytechnic Institute of Paris in France. And today I'd like to present you some of my latest research entitled Improve Convolutional Neural Networks Pruning by Maximizing Filter Variety. So maybe a bit of context before starting. As you probably all know, neural networks have been at the center of most research fields, such as language, vision, games, and so on. And over the last few years, they have been involving more and more parameters, following a trend that's quite similar to the Moore's law, but with parameters, if that makes sense. And the main challenge with that is it makes it very difficult for deployment on embedded devices or on highly requested remote servers. But luckily for us, a field of neural network compression is quite active over the last few years. And one of those techniques that is best known is the neural network pruning, and consists in removing useless parameters in a neural network. So in the case of neural network pruning, there exist several axes of development. One of those axes is called the pruning granularity, and is concerned about the shapes of blocks that are removed in each network. In the case of CNN, we have several ways to remove those blocks of parameters. Sorry, you can remove either by weights. So the decision about weight to remove is done individually, leading to sparse matrices and sparse filters. But we can also remove entire vectors or even complete convolutional filters. The more structured we are in the pruning, the most difficult it will be to select the weights precisely. So it will witness a bigger drop in performance, but it will be easier to implement and to take advantage of in terms of speed of and compression, because it doesn't require dedicated hardware of software. For this reason, we consider filter pruning in this research. A second axis of development of pruning is the schedule, which is concerned about the way the pruning is performed during the training. And the first proposed schedule was called a one-shot pruning and consisted in starting from a pre-trained network and pruning it in one shot, and maybe fine-tuning a bit to recover from the lost performance. But nowadays, the most widely spread schedule is called iterative pruning. It consists in 3 steps. The first one is to train the network to completion, then to remove the weights that are considered to be the least important. In practice, this is done by applying a binary mask, which values are either 1 or 0, according to if we want to remove the weights or not, and then to fine-tune the network to recover from the loss of performance. By doing step 2 and 3 iteratively, we can then get our final and pruned network. The last axis of differentiation in pruning is the criteria. We saw the granularity and how to remove the weights in a network, the schedule and when to remove the weights in the network, but we still need to assess which weights are considered to be more important than others. The criteria is maybe the most active field in the pruning, and I've only represented here 3 most common criteria of selection of weights. So you can see in abscissa and ordinate the values of weights before and after training, and as you can see, those are quite correlated. The most silly way to remove the weights is random pruning, which consists of removing, as the name suggests, removing random weights in the network. And maybe it seems simple, but it can already reach non-trivial level of sparsity in a network because of the over-parameterization of most of the network. A second criteria, which maybe is the most used in the literature, maybe 90% of the time used in the literature, is the L1 norm pruning. This criteria says that the weights which have the lowest magnitude are considered as less important than the others because they produce weaker activation and thus participate less in the final results of the network. But this L1 pruning has shown some limitations, particularly in the case of the fine-tuning regime, which is why the movement pruning has been introduced. The movement pruning takes into account more training dynamics because it considers that the weights whose magnitude has increased during the training are more important than those whose magnitude has decreased during the training. So the main problem that we want to tackle is that in the regular pruning algorithm, the most commonly used criteria has no incentive to reduce the filter redundancy and to keep a wide variety of filters. Indeed, if two similar filters have the same norm, L1 norm, for example, both of them will be either kept or removed, regardless of their individual role in the network. So what we propose in our research is to add a fourth step in the pruning technique, forcing the criteria to remove redundant filters and to keep a wide variety of the filters. This is a clustering step that is applied just before the pruning one. This clustering step is using an activation maximization technique, which is a technique generating an image which maximizes the activation of a given filter. So this image represents the feature that a given filter is the most sensitive to. So basically what we can do is to apply activation maximization on all the filters of our network, producing the corresponding features, encode those features into a CNN, and then apply k-means clustering on those generated features. The goal here is to cluster filters by similar functionalities. We thus have several clusters with redundant weights and redundant filters, but also cluster with only a single filter, meaning that the filter in that cluster is very rare and maybe should be kept because it can have importance later on in the network. We choose the parameter k, the number of cluster, according to the desired sparsity. As we want to keep a single filter per group, the parameter k is chosen accordingly. So let's say we have 64 filters and we want to reach 50% sparsity, then we will have 32 clusters and thus only have 32 remaining filters. Here is a qualitative comparison of the criteria L1 norm and movement with and without the addition of our clustering technique. I don't know if you can clearly see, but I have highlighted in red, green, and blue the most commonly, the most present cluster of features. And as you can see, in L1 norm and movement, a lot of redundant filters are kept, which is not the case when using the clustering beforehand. Also, some of rare filters, such as these blue and yellow patches, are remains when using the clustering techniques, and this was not the case without. So we can see that the addition of the clustering technique helps to reduce the redundancy of remaining filters, but also to keep a variety as wide as possible. We validate our method on different datasets and architecture, such as CIFAR 10, 100, and Caltech 101, and for two models, VGG16 and Resonant 18. The training procedure that we follow is pretty common. We start from network pre-train and ImageNet, and apply basic data augmentation. The pruning procedure that we follow is filter pruning. The criteria that are applied in each of those clusters are L1 norm and movement pruning. The schedule is iterative, and we validate for 3-level sparsities. So here are the tables of the results when using and not the clustering technique, and we can see that in most cases, for the architectures, different levels of sparsity and different data sets, it is beneficial to add this clustering technique before applying our pruning criteria. We also conduct another experiment based on the lottery ticket hypothesis, which I don't know if most of you are familiar with, so I will explain briefly. Lottery tickets is an hypothesis that has been proposed very recently and goes as follows. In most neural networks, there exists a subnetwork that is at least as efficient and can be trained at least as fast as the complete neural network, as long as it starts from the same initialization. Authors have since then weakened a bit their hypothesis because it was not proven to be true for big data sets or architectures, and proposed the lottery ticket with rewinding, which instead of starting from the initialization, start from the value of weight a bit later during the training. So these experiments consisted in 5 steps. So very similar to the iterative pruning procedure. We start from a freshly initialized network and train it for some iteration and save the set of values of weights. We then train it to completion, apply the pruning, and instead of continuing the training, we restart the value of the weights to the saved values that we saved before. By doing so for several iterations, we extract what is called a winning ticket, and corresponds to the network that should be at least as efficient and train at least as fast as the complete network. So by doing the experiment, what we want to show is we want to compare if the tickets that we find with our technique are from a good quality or better than the ticket that are found with a common criteria. So here you can see the accuracy for different level of sparsities, and in the curve in orange is when applying the clustering technique. And we can see that in most cases and for most sparsity levels, the application of the clustering technique helps to find better performing winning tickets. So to conclude, we propose an extra step in the iterative pruning schedule, which is a clustering of the features of the filters in a network. The goal of this clustering technique is to help the network to keep a variety of filters as wide as possible and reduce the redundancy of the remaining filters. Those results are validated on 3 datasets and 2 architectures, and we saw that it helped to get better performance than common pruning criteria, but also to find better performing winning tickets. Thank you very much. If you want to, I posted 2 links to the code that is used for those experiments, but also to my website where I post regularly articles about neural network pruning if you're interested. Thank you very much.
Okay, let's thank the speaker. There's just room for 1 question.
Yes.
Please.
Hi, thank you for your presentation. Actually, I have many questions, so I will come back to you later on. I just remain with one. Have you tried your technique with more complex data set, let's say, for instance, ImageNet? Because in the past, I tried something very similar, and it was not working as well on larger scale data set. Thanks.
Yeah, that's a good question. I'm aware of the fact that we try only on 3 data sets, but what I found in like Cypher 10 and Cypher 100 are kind of toy data set that you cannot generalize to bigger data sets such as ImageNet. But what I found is that it was mostly the case with when training on Caltech 101. You can basically Caltech 101 is a bit bigger than Cypher 10, especially in the resolution of images. So this is the biggest data set that we train on. And the problem with training in ImageNet is because we start from networks that are pre-trained on ImageNet, it can pose problems. But I agree with you that that's a good question. And this is Caltech 101 is the biggest data set that we tried our experiments on.
Okay. No room for further questions. You can meet elsewhere, of course. Let's move to the next speaker. Contrastive supervised distillation for continual representation learning. The speaker is Niccolo Biondi. Remember all of the speakers, 12 minutes for presentation, so we can have some room for questions, so thank you.
Okay, hi, my name is Niccolo Biondi, and I'm going to present contrastive supervised distillation for continual representation learning. This is a joint work with my colleagues Tommaso Barletti, Federico Pernici, Matteo Bruni, and Alberto Del Bimbo from the University of Florence. Visual search systems address the problem of finding similar images in a large indexed gallery set by matching query features with gallery ones according to certain distance functions. Recently, DCNNs have significantly advanced the task of visual search by learning powerful feature representation from data. Typically, these models are trained on static dataset. That means that all the data is available during the training of the model. However, this condition is restrictive in real-world application, as new data is constantly emerging, and updating this model several times on both old and new data is time-consuming. Furthermore, static datasets have typically several privacy or ethical issues which affect modern AI systems. So in this work, we develop visual search system based on continual representation learning. That means that we aim to do not forget the already learned representations while learning incremental data. With continual representation learning, part of the benefits are that data is not stored on private servers and that the computation is distributed over time. However, the main issue when learning incrementally is the catastrophic forgetting. That is a performance degradation on previous search tasks when new knowledge is assimilated. As you can see from the figure, when the model is trained on the first task, the performances correctly increase. But when the model is updated on a new task, the performance on this task increases in the yellow curve, while the performance of the initial task decreases, showing catastrophic forgetting. As expected, this behavior is also observed in the other tasks. Catastrophic forgetting is also related to the stability plasticity dilemma. That is a trade-off on how much the model has to learn new data and how much the model has to preserve the previously acquired knowledge. Indeed, too much plasticity leads to forgetting, and too much stability impairs adaptation. Furthermore, there is recent work that provides empirical evidence on the fact that feature forgetting seems as not catastrophic as classification forgetting. That means that in visual search tasks, this can be so relevant because it is based on features. And we argue that this empirical evidence can be exploited in technique which update models without using any old data, that is in a memory-free settings. However, to better comprehend the difference between the continual learning and the continual representation learning, we now highlight the difference between these learning settings. First, the evaluation method in visual search do not use the classification accuracy. Second is that visual search data have typically a finer granularity with respect to categorical data that is used in classification. And the third is that no classes are required to be specifically learned. Indeed, in continual representation learning, we don't care about classes. We only care about learning internal feature representation. So this different origin between the classification and the forgetting and the feature forgetting can be relevant for develop memory-free continual representation learning method and for the inherent visual search task. So we propose a new memory-free distillation method for the continual representation learning task, in which we mitigate the feature forgetting while learning discriminate feature. We call our method Contrastive Supervised Distillation. CSD aligns current and previous features of the same classes while at the same time pushing away features of different classes. In particular, we follow the basic working principle of contrastive laws used in self-supervised learning. And in order to leverage label information that is present in new data, we replace the anchor features with the feature of the teacher model, that is the model learned at the previous task. Indeed, our framework is based on the teacher-student framework, in which the teacher is used to preserve the previously acquired knowledge during the training of the student, that is the current model, in order, in fact, that all data is no more available. So in order to learn the new incoming data, we define the plasticity loss as the composition of the cross entropy and the triplet loss, while in order to preserve the knowledge, we define the stability loss as a composition of the knowledge distillation penalty and the CSD component. Here in the bottom, you can see the overall loss that is optimizing in our framework, and in the figure, we highlight the 4 losses and the components that are used to compute them. In particular, CSD aligns the student feature vectors of the same classes to their respective features extracted with the teacher model, and push away features of different classes. In particular, we define the anchor feature as the teacher features. And given an anchor, we define its positive sample as the feature of the student that are of the same class with respect to the anchor, while we define the negative samples as the feature student that belongs to other classes with respect to the anchor. Here in the figure, you can see with the superscript prime and in blue code the feature of the teacher, while in the orange there are the feature of the student. The red arrows indicates the negative sample that are pushed away from the anchor, and the green arrows indicate the positive sample that are aligned to the anchor. And the animation shows how CSD works. More formally, by the formula, you can see that CSD minimize the cosine distance between each anchor, Fi prime, and its positive sample, while maximizing the cosine distance between the anchor and its negative sample. In our experimental result, we adopted the recall at 1 as the evaluation metric. The recall of 1 measured the proportion of query vectors for which the nearest neighbor is ranked in the first position. In particular, in the figure on the right, you can see an example in which the recall at 1 is 33%, as only the second example is correctly ranked in the first position of the ranked list. In order to compare CSD with several baseline and current state-of-the-art methods, we adopt 3 different datasets that are Cypher 100 and 2 fine-grained datasets that are Stanford Dogs and CAB 200. In particular, for the 2-task setting, we firstly trained the DCNN with the first 50 classes of Cypher, and then we evaluate it on the first 50 classes of the test set of Cypher, obtaining an initial model which achieves 67 of recall at 1 on the initial task. After that, we update the model with several techniques and using only the second task without any data from the initial task. After that, we again evaluate it on the first and the second task set, obtaining this result. Our method achieves the highest values on both the initial and the second task when compared to methods that try to mitigate the forgetting, being second only on the second task with respect to the fine-tuning, which, however, focuses only on learning new incoming data. This result in our method achieving the highest average recall at 1. In Cypher, there is a huge gap between the continual representation learning technique and the joint training, that is the upper bound. And this is probably due to the fact that in Cypher there is a huge dataset shift across tasks. For the 2-task fine-grained evaluation on the fine-grained datasets, we obtain similar performance with respect to the Cypher, as our method achieves always the highest values when compared to the other methods, being second only on the second task of Stanford Dogs, with a gap of 0.2% with respect to the fine-tuning again. However, in the fine-grained dataset, we obtain similar and comparable performance with respect to the joint training. And this is a really interesting result, as probably there is a lower dataset shift, and this result in a lower feature forgetting. In the more challenging scenario of a multi-model update, in which we update the models several times and we evaluate it on the initial task set of the first task, that is done in order to observe how the model preserves the knowledge, the previously acquired knowledge after several model updates. We obtain the highest values on both Cypher and fine-grained dataset, how you can see from the left and the right plot, respectively. In particular, in the fine-grained dataset, we obtain comparable performance with respect to the upper bound, and we outperform current state-of-the-art method by a large margin, that is more than 20 points of recall at 1. As a conclusion, we proposed contrastive supervised distillation to reduce feature forgetting in continual representation learning without using any old data when update the model. Experimental results show the advantages provided by our method in both single and multi-model update. In addition to this, the experiments also confirm that feature forgetting is not as catastrophic as classification task, as we obtain similar performance with respect to the upper bound. So thanks for listening and for the award that we received.
Okay, let's thank the speaker for his nice presentation. Okay, there's room for some questions. Please.
Yeah, thank you for your presentation. Very interesting. I have a couple of questions, very quick. Did you try in the first task to use less than half of the datasets? And maybe does it matter if you use less data in the first task, and then go on with the other, compared to your setup, which is usually half and half, if I remember. The other question is, yeah, I have to think about it.
Thanks for the question. Yeah.
Okay.
Very interesting point. Yeah, actually, we tested both the scenario. That is, in this plot we report the case of which we evaluate the model starting in the first step from the alpha of the training set. That is, for Cypher, we start in the initial task with the 50 classes, and then we update with several classes. And in CAB, we start in the initial training set with 100 classes, and then we update. But in our experimental result, we conducted also other experiment on divided the training set with task set with the same number of classes, and the experiment confirmed that these results. So, yeah.
Okay, and the other questions? In your last formulation, the contrastive one, you said that you only have negatives in the contrastive, in the uniformity term. Is that correct?
Here.
Yes.
Yeah.
Do you only have negatives?
No. Here in the numerator there is the positive sample. There are the positive samples.
But in the denominator?
Yeah.
Sorry.
In the denominator, yeah. Sorry.
Only negatives?
Only negatives.
Okay.
Yeah.
Thank you.
Okay. One question again.
Hi. Also, my question is about the contrastive loss. In particular, how did you select the distant example? In a random way or something like that?
No, we use the label information. That is, positive sample is the sample of the same class with respect to the anchor. And the negative are the other samples, which belongs to different classes.
Okay, thank you.
Thank you.
Okay. Just one quick question from me. What about the computational complexity? At which point we are for implementing this in real time?
I think that this is a really interesting point. We actually we conduct an ablation study on our method, evaluating the loss component that are used to preserve the knowledge. And we actually observed that when using all the 4 losses that I know they are many losses maybe, but it is the best possible combination. So, well, yeah, that is the only way to do not use previously data. So.
Okay, thank you very much.
Thank you again. Bye bye.
Okay, let's thank once again the speaker. And now we move to the third one. Fusion of periocular deep features in a dual input CNN for biometric recognition. The speaker is Luisa Cimino. Lucia. Are you ready? Lucia. Okay.
Presentazione a schermo intero, per favore. Ctrl L.
Okay. Hello, everybody. I am Lucia Cimino, and today I'm here to present my work, Fusion of Periocular Deep Features in a Dual Input CNN for Biometric Recognition. Before to start, I want to thank my co-authors, Professors Andrea Abate, Michele Nappi, and Fabio Narducci. In recent years, periocular recognition has attracted more and more attention. With the explosion of the COVID-19 pandemic, facial recognition has become problematic due to introduction of the facial masks. The occlusions of the lower part of the face leads to the loss of more than half of the biometric information in the human face. So the extensive use of the face as a biometric trait also in several daily applications made it necessary to adapt facial recognition systems to this new way of living. This adaptation can be realized by allowing standard facial recognition systems to identify subjects based on the periocular area, which is the only area that is not covered by facial masks. In addition to being resilient to the mask occlusions, the periocular region is also a reasonable trade-off between iris and face-based biometrics, as the first one required a high level of collaboration to the respect of the face recognition. Plus, furthermore, but the most important drawback in this case is that obviously we have a loss of accuracy for the periocular recognition with the respect of the face recognition. Okay, so the idea in this work is to implement a dual input neural network model in order to recognize the subject considering the solely periocular area of the face covered by a facial masks. More in details, we have a Siamese-like CNN model that consisting into two parallel streams, which are two parallel CNN models, identical, which compute the input separately, inputs that are represented by the left and the right eye, respectively. The goal here is to explore the information aggregation for the periocular area and to determine the impact of the combination of the features in the periocular region. In this case, the aggregation is represented by the type of the fusion level of the fusion layer employed in our model. In this case, we consider three different fusion layers, which are maximum, average, and concatenation layers. So, the proposed model consists of these two identical CNN models that are composed of 4 convolutional layers, 3 max pooling layers, and a final flattened layer to prepare the input for the fusion. The two outputs of the convolutional base models are combined through a fusion layer, which can be maximum, average, or concatenation fusion layer, and at the end, a fully connected layers are added after the fusion to properly classify the subjects. So the experiments are carried out on M2FRAD dataset, the mobile masked face recognition database, which is a frontal face multimodal database, including digital videos of 46 subjects with shot with and without facial masks. The most important characteristic of this dataset is that the acquisition were made by the subject with their own mobile device. So we have a dataset which is cross-platform in the wild dataset. So it's a challenging dataset in this sense. Okay, prior to being input in the model, the data has been preprocessed. Considering that the M2FRAD dataset is a video dataset, obviously a collection of 10 frames were sampled from the videos. Also, the periocular region, since the videos shot all the faces, not only the periocular area, the periocular region is cut out from the face, and a split into either left and right eye is also applied in order to have the two inputs for the model. The final images, which represent the two inputs, are RGB images of 80 per 80 pixels. Okay, all the experimentation have the same configuration, so a batch size of 64 and 20 epochs for training process, and the data were divided into a typical 70-30 ratio. Metrics like accuracy, precision, recall, and F1 score are considered to evaluate the model. Plus, base model is applied also on the single left and right eye in order to better highlight the motivation behind the adaptation of a fusion model. So we tried the model, only the base model with the left and right eye, and then we explored the performance on the fusion of the eyes. So the performance achieved by applying the base model on the left and right eye separately are more or less the same. So they show the gross performance in comparison with the adoption of the fusion model, as we can see from the table, with an accuracy score of 0.87. Okay, a little bit, so for the metrics, we have the same results. A little bit change can be observed in the rock curves, in which we can observe an IUC score slightly better for the left eye, which 0.89 instead of 0.88 for the right eye. The fusion model, in general, achieve better results with respect to the left and right eye separately, but we can see also different performance between the different fusion strategy that we applied, so different performance for maximum average and concatenation layer. So focusing on this part of the experimentation, we can see that the best fusion layer is the concatenation layer, which achieved the best performance with a 0.97 of accuracy. Also for the equal error rate, we have an equal error rate of 0.08. Then we have the average fusion level, that is the second one. We have an accuracy of 0.95, so it is a little bit worse than the concatenation layer, but we have acceptable metrics in this case. And the equal error rate in this case is 0.14. The last but not least maximum fusion layer, which is the ROST, with an accuracy of 0.90 and an equal error rate, which is a little bit similar with the average one, because we have a 0.15 equal error rate. So in this case, with the maximum fusion layer, we have gross performance in comparison with the case average versus concatenation layer. So we have a little bit of decrease. Okay, we can see we can see the metrics. We can see the metrics that reflect the rock curves reflect the metrics, the results achieved with the metrics. So we have an IUC score that is higher for the concatenation layers, obviously, that reached the 0.097, and it is followed by average fusion layer and maximum fusion layer. Okay, so in conclusion, this work proposes a dual input CNN which takes an RGB images of the left and right eye and of the same periocular region as input for the periocular recognition in an uncontrolled environment. Experiments were performed on M2F RID dataset using 3 different fusion layers with the same overall architecture in order to evaluate the most suitable fusion layer for the aggregation of the information. It can be observed that the fusion layer that is the best is the concatenation layer with an accuracy of 97%, and with respect of the fusion contributes by adding up a 10% of recognition accuracy with respect to the base model applied with the separate input. In future works, a benchmark operation, including also their data set, can be applied in order to test the behavior of this kind of network in different conditions and with a higher number of subjects.
Okay,
thank you.
Let's thank the speaker. Well, there's room for some questions, please. No questions? I have one for you.
Okay.
Okay, just a curiosity from my side, what about the scalability of the process? Because, for example, if you extend the number of people, you have some novel people to enroll, which is the impact on your network?
Okay, we consider this as a future works to extend in this sense, but we are confident that the method will be scalable in this sense. So we will see, but we are confident on this way.
Okay. Other questions? Okay, in this case, let's thank once again the speaker. And we can move to the next talk. Automatic classification of fresco fragments, a machine and deep learning study. The speaker is Lucia Cascone.
Il tasto avvia presentazione. Ok, perfetto. Un attimo lo mettiamo anche sullo schermo.
Ah, ok. Ok. Perfect. So, good afternoon. I am Lucia Cascone, a PhD student of the University of Salerno, Italy. Today is with great pleasure that I introduce you the work Automatic Classification of Fresco Fragments, Machine and Deep Learning Study, a joint work between the University of Salerno and the University of Pavia. In this work, we want to propose a study about the problem of mixed fresco fragments classification, an important and preliminary step in the reconstruction of broken frescoes, especially useful when we have hundreds of fragments that must be discriminated. In particular, this problem can be considered as a particular and relatively new case of stylistic classification, where when we have only a small subpart of the entire artwork. We propose a comparison between different machine and deep learning approaches with the objective to find out which are the best performing solutions and also to provide a valuable baseline for researchers in this working in this field. In particular, the work is divided as follows. We have an introduction to the problem, explanation about the method, the tested conditions, and the data that are available for this task, a discussion about the experimental results, and finally the conclusion. So, the problem of reconstruction of a fresco is a challenging task that requires a great effort from art experts and also restorers to be properly handled. Very small fragments, irregular shape, color changes are just some of the possible problems that can occur in this kind of task. So for this reason, a general and good solution able to deal with all the complexities of this problem has yet to be found. In general, in fact, in a real scenario, such as a church destroyed by an earthquake or by war bombing, it is likely that pieces of different frescoes, which were close on the same wall, ended up mixing together, making their reconstruction more complex. So it would be very difficult to separate them if there are many of them or no. Very old reference images of the original frescoes, such as for Roman or Greek artworks. So, for this reason, we want to treat this problem as a special case of stylistic classification, where the artwork is not intact but divided into small pieces, with even some parts missing. Our hypothesis is to establish methods, it's to find methods for classifying artworks based on the artist's style, and when it's available, only a small portion of them. So in general, we have three main goals, practical and theoretical ones. We want to provide a useful tool to assist restorers in their work. We want to study if there is a specific stylistic classification strategy that can be used even when only a portion of the artwork is available. And we want to find also what is the best approach between machine and deep learning. To do this, we use the Daphne dataset that is the largest collection of images of artificial fragments of artworks, and it contains 62 frescoes ranging from the 14th to the 18th century, made by 28 different authors. For each fresco, we have 18 different fragmentations that contain spurious fragments. No spoiler. So we chose for each fresco the fragmentation with more fragments available and no spurious data. In particular, the number of authors is not equally distributed in the dataset. So for this reason, we selected just the authors for which at least 4 frescoes with enough number of fragments were available, and so for this reason we selected Fra Angelico, Giotto and Michelangelo as authors, while for the task of period classification we selected the 14th, 15th and 16th centuries because the most suitable artworks belong to these periods. So in this figure, we report a simplified schema about the deep learning approach. After the loading of data and a resize step that it was necessary to have in order to have the same sites we applied also a technique of data augmentation to enlarge the variety of our data set, while for the future extraction we tested the convolutional layer of both VGG16 and ResNet34 pre-trained on ImageNet, that it's a famous data set. For the machine learning approach instead, we implemented three, and we used three very famous classifiers: random forest, support vector machine, and KNN. And in particular, due to the limited size of the fragments and so the consequent lack of information, we decided to extract three visual features in terms of color, shape, and texture. So for the tested conditions, we focused on two classification approaches, per-author and per-period. In the first one, we discriminate fresco fragments basing on the style and the characteristics of a specific artist, while for the second approach, we do this but on common stylistic features of a period. For the first one, so for the first approach, we imaged two different scenarios. A scenario where we have all the fragments mixed together, or the second one, or a scenario where we have only partially mixed. For example, we can imagine that the first one is the most complex because the fragments of frescoes used in the training are older than those used in the testing set. And we imagine a scenario where we have a wall that is totally collapsed. While in the second one, we imagine a situation where this wall is only partially collapsed, and so we have also an information about a part of it. The second one we name a random split, where fragments of the same fresco can be present both in training and testing set. For the second approach, period, we implemented only the second strategy because we need a proper number of samples and authors to properly to have a proper training. For the experimental setting for machine learning strategy, we applied an exhaustive search for the hyperparameters. We chose a configuration, a set of hyperparameters, and then after, through an exhaustive search, we selected the best configuration. To avoid overfitting, we implemented also a k-fold strategy with a k-value set between 2 and 10, while for the deep learning strategy, we split the data set between the classing, training, validation, and test set. The learning rate, it was low, and we used another optimizer. About the results, as we expected, this approach with this scenario achieved the worst accuracies because we can observe in general that the best solution was a machine learning approach. And we can see this also in the figure, because in the image we report the best accuracy both for deep learning and machine learning approach. And we can observe how machine learning outperforms the deep learning approach. And for more or less all the categories, just for Frangelico and Michelangelo, we can observe how the accuracies are more or less are close. Why this? Probably because the samples of these two authors were very different in terms of colors. And so this maybe can help the model to discriminate between them. In general, we can observe that we have a F1 score that is over the 80% for all the classification tasks, and that the random forest is probably the best solution, because also for the first category, it has not the highest result, but however it was the second, and it was more or less the same. For the random split, we can observe, as we expected, that the accuracies are better, but in general, also in this case, we can we can observe how random forest is the best solution also for this kind of approach and scenario. Also here, the deep learning approach is probably not the best solution for this kind of problem, and especially for this kind of problem, also because we have a training set with a limited size. Because for this approach, for the peer period approach, the situation is totally different. And this maybe is also due to the fact that we have a lot of samples in this, for this approach in the training set. And so we give the possibility to the model to learn from them. Here we can observe how between ResNet and VGG, VGG is the best solution. However, also the machine learning approach achieves a good results in general. So, summarizing, we can say that machine learning classifiers can achieve a level of performance comparable or even higher than that of complex deep learning architectures, that for a machine learning approach, probably random forest is the best solution, because it is an ensemble learning that could overcome the limitation of representation of the input. And that for the deep learning approach, VGG architecture performed generally better than the ResNet one. And for random forest, we have a F1 score that is almost always over 80%, and in some cases also over 90%. And this is interesting. And finally, that for fresco split, that is the first scenario for our first approach, machine learning classifiers can outperform deep learning solution when only few samples per author are available. So, thanks for the attention.
Thanks to the speaker. Well, some questions? Any questions?
Hi, thank you for the presentation. I have two questions. One more technical, the other is more curiosity. The first one is, have you considered the use of some more specific loss when training this model? Let's say, I assume, or probably I lost it, that you use the cross-entropy loss for the training the task. Have you considered to use style loss, for instance, which is typically used for GAN, I know, but...
Yeah, as I said, in this first work, our aim was to provide a valuable and performing baseline for this kind of problem. We are working on, and in our study, we are also putting attention in this sense, and also about the interpretability and about the test samples, because we want also to investigate when there are errors, why? Okay. So yes, we are working on this.
Okay, and the second, which is curiosity, in the sense of interpretability, have you thought that maybe your strategy can work to detect also fakes? Let's say I go to someone and I commission to make some artwork which resembles, let's say, Giotto, and maybe it's not?
Maybe I didn't catch the question.
Okay, maybe we can talk later then. Thanks.
Okay.
Other questions? Okay, I have just I've got a question for you. I noticed that you, in the first part of your presentation, mentioned that you try to model the problem as a sort of authorship by pointing out the differences, the characteristics of the author. Why? Which insight suggests you this way to model the problem?
Also because we have also a collaboration with other experts, also art experts, that suggested us, for example, now we are working also on this, to give to give more weight on specific features for another with respect than another one. For example, if this is not the case, but for example, for Roman artworks, the color is very important because we have a particular color that is the red, that it's very famous, that it's really typical of this period. And so in general, we are also trying to speak with the art experts and the restores to so in the future work we want also to give a different weight to the features, basing also on the authors and the characteristics.
Okay, thank you for your answer. Let's thank once again the speaker. Okay, we can move to the next presentation. This is a remote presentation, unsupervised deformable image registration in a landmark scarcity scenario, choroid OCTA. Is the speaker here? Okay, you are with
Hello.
us. Hello, hello. Your name?
I don't know if Emilio.
Okay, Emilio.
I don't know if you can see my screen.
Yes, we can see you, not your screen.
Okay. Now, maybe?
Now, all right. Let's move to the presentation style. Okay, we can start. Thank you. 12 minutes and then questions for you.
Okay, thanks. So, hello. I'm Emilio Lopez Corella. I am here to present you this paper entitled Unsupervised Deformable Image Registration in a landmark scarcity scenario, choroid OCTA. This work was elaborated by the authors that you can see here. So in this work, as a previous summary, we propose a deformable registration methodology to try to align inconsistencies that are generated when obtaining angiographic optical coherence tomography, or OCTA images. So to give you a little bit of context, what is OCTA imaging? OCTA imaging is a non-invasive imaging modality that is obtained by temporal contrast of the OCTA imaging. It therefore shows a greater intensity in those areas that change over time, such as, for example, vascular areas. Recently, this type of image has begun to be used in areas deeper than the retinal layers, at the level of the choroid. So an imaging at this level of the choroid looks like the one you see here. It is a very granular image where vascular areas are shown in white and gray, and avascular areas, also known as flow voids, are shown in black. The interesting thing here is that the distribution of these flow voids has been correlated with the occurrence of multiple disease. So it has a special interest and great potential to be used as a biomarker. The problem is that this type of image has many local deformation and inconsistencies. When these images were captured over long time periods of weeks or months that are typical during monitoring a disease or a treatment. This greatly affects when comparing the distribution of flow voids over time. Furthermore, this also implies that a pixel-to-pixel comparison of the images is unapproachable unless these inconsistencies are corrected. So, to solve these inconsistencies and to be able to compare the distribution of flow voids in a proper way, one could, for example, make a deformable image registration. But these images contain features and characteristics that greatly affect the performance of this registration. First of all, the characteristics I mentioned before. They are very raw image with a granular appearance and multiple local deformations. Besides, in contrast to other imaging modalities as MRA, this imaging modality does not present large, efficient, and representative structures that appear in all images. For example, when you scan a brain, you can see typical structures, but here not. And furthermore, in clinical use, is typical use high resolution images, which present a larger displacement in the deformations and make them more difficult to resolve. So, taking all these factors into account, and to be able to compare images obtained in different time instances, we propose an approach to perform this deformable registration. Our approach is based on using a convolutional neural network trained in a unsupervised manner. To train the network and solve this registration, we use a dataset from a previous clinical study, where 52 patients with central serous coronopathy were follow up during a laser treatment. For each of these patients, images of both eyes, healthy and diseased eyes, were taken at 4 different time instances, which this instance which you can see in this image. This instance corresponds to the instant pre-treatment, 2 days after the laser treatment, 1 month after the treatment, and 3 months after the treatment. You can see that the image of instant 2 is the one corresponding to the days after treatment because of the gray area with amount black pixels. Okay, so then we designed this neural architecture that you see here. This is basically composed of C branches that serve to carry out the deformable registration. A low resolution branch, where most of the convolutions, downsamplings, and etc. are performed, that serve to obtain the low futures that define the longest displacement in the image. On the other hand, the medium and high resolution branches are used to refine the futures of the low resolution branch, and besides to detect more subtle displacements. Each block in this architecture is composed of 2 concatenated series of convolutional layer and batch normalization layer and liquid relu layer. At the end of this first part of the network, a series of extra convolutions are applied to refine the final result until the flow file is obtained. This flow file, with the image to be moved, is passed to the spatial transformer as input that gives the final image result. So, well, in this slide, you can see the details of the training. Here you can see, for example, that we use as loss the local normalized cross correlation. Besides, we use a quite exhaustive data augmentation to improve the generalization of the network. This augmentation includes elastic transforms, blur, noise addition, and alerts, etc. Here you can see to prove the efficacy of the model as a baseline, we use this series of widely used registration methodologies. As evaluation metrics, we use this set of different distance metrics that you have defined here. So we go to with the results. Then let's look the results we had here in this table. In this table, you have the comparison of the different metrics obtained between our method and the baseline methods. As you can see, our network obtains better metrics in all the metrics used. Besides, it's more efficient in time. And more visual example is here in this slides. Here is an example of applying the different registration methods to the same 2 images. In the first row, you have the original image without a line. In the third column, you have the different image. The different image is a pixel-to-pixel comparison where darker pixels in the first image are represented in red. The darker pixels in the second image are represented in blue. And pixels that are the same in both images are represented in white. You can see how our methods manage to eliminate the inconsistencies between the image in a natural way, without creating artificial or strangle distortions, while leaving the really significant change intact in a more efficient way comparing to the other tested methods. Finally, here are more examples with more image when we apply our methods. Here, our method is applied to image obtaining a different time instance. We can see how, well, we have pre-training and post-training images, pre-training and 1 month images, pre-training and 3 months images, and etc. So we can see how in all cases our method allows a better comparison of the distribution of flow voice, which will lead to an improvement in its efficacy as a biomarker, and besides an increment in this visualization. Our methodology is applied in this case, in this specific case, but this methodology can therefore use it in a complementary way to others type of methodologies like cementation or other tasks to improve the monitoring of a pathology or a treatment. As in our case, is the laser treatment, for example, of these patients with central serous coronopathy. Also, we have dealt with the specific problems of this type of image. The use of the registration methodology is extensible to other similar imaging modalities, especially to other modalities that have these type of characteristics, like these granular and multiple and numerous local deformations. So, well, I hope you enjoy the presentation, and thank you very much for your attention. Hello.
Here, some questions for the speaker. Any questions? I have a question for you. Since we have some time, could you better explain us which kind of noise is in these images? Because we are not experts in the field, so it could be useful for us just to understand in these images which are the defects and the artifacts that your method allowed to remove. Thank you.
What defects and artifacts my method avoid to remove or allow to remove? Can you repeat, please? I don't know if the connection is. Hello?
It cannot hear me. Emilio?
Yes, now yes.
Emilio? Okay.
Yes,
okay.
Yes.
Okay. The question was if you can just explain better in this slide which kind of artifacts your method allowed to remove so that the expert, the human expert, can analyze these images better. Thank you.
Yes. The problem with this image is that the artifacts are very small, and there is not a big thing. It's more that numerous, multiple small displacements. So when you try to, in this case, for example, the dark regions are extracted to use a biomarker. But when you try to compare one image to another, distribution of these dark regions can change a lot because there exist these multiple small changes. So in this network, like you can see here, there exists plenty of white zones because the network is aligned each point with each point that have minimal differences. But the important thing is do this without lost the significant changes that are the flow voids or the dark regions. Because, for example, in here you can see that the red areas here is maintained because there is a different because they apply a treatment. I don't know if I explain.
Okay,
well.
it's just clearer than before. Thank you. Thank you very much. Okay, any other questions for the speaker? Okay, no question for you. Thank you for your talk. Okay?
Okay, thanks. Bye.
Let's thank the speaker once again. Okay, we have the last presentation for today. The title is Unitochest, a lung image dataset for segmentation of cancerous nodules on CT scans. I invite the speaker to join us and to upload her presentation.
If you need full screen, Control L. Control L.
Okay.
Hello everyone, my name is Hafiz Aisha Chaudhary and today I'll be presenting Unitochest, which is a novel lung CT scan dataset with annotated lung nodules. And I'll also present a methodology to segment and detect the cancerous lung nodules from the said dataset. I will start off my presentation with a little bit of introduction as my research is from the medical background. So to get everyone on board, we will have a little bit of background. Then I will move on to introducing the data set that we are presenting today. I will also cover the comparison between our data set and the similar state-of-the-art data set that is already available. Then I will introduce the methodology that we have used to segment and detect the lung nodules and what are the results that we have achieved using our methodology. Okay, let's start off with a little bit of introduction. I think everyone is familiar with the cancer disease and how it works. I think the most talked about cancers are breast cancer and prostate cancer, but you might be surprised to know that lung cancer has become one of the leading causes of death in both male and female in 2021, with the survival rate as low as 14 to 15% in the later stages. The key of survival is the early diagnosis and treatment of lung cancer. So lung cancer is usually when a patient develops cancerous nodules in the lungs. In this cancer, the doctor suggests the patient to get medical imaging done In lung cancer, we do CT scans, which are computed tomography. It is done in the abdominal area, in the axial plane, and lung CT scan slices are produced into 2D format. An example of such CT scan slice can be seen on the screen. From these CT scan slices, the radiologist further detects whether there is a cancerous lung nodule present in the CT scan and then suggests any kind of treatment. This manual lung analysis is not only time consuming, but it's also prone to inter-observer variability. To remove this problem and to automate the whole system, CAD systems are introduced. CAD systems are basically computer-aided diagnosis systems which use learning-based methods. These learning-based methods use medical imaging data and they detect whether there is a cancer present in them. And if the said cancer is detected, then the further localization and the segmentation of the cancerous region is done. So as we know that learning-based methods are only as good as the medical or any kind of training data that is provided to them. In our case, it is medical imaging data. So for those of you who are familiar with medical images, we know that medical images are not only very expensive to produce, but they're also very large in size. Once they're produced, then the further cleaning and the all of the private information of the patient has to be removed from those images, and they have to be annotated by a specialist. So we not only need a large medical imaging data set, we need a large and good annotated medical data set for the CAD systems to work efficiently. When we talk about good annotated data set, we directly go to the state-of-the-art data set for lung cancer detection that is available. It is LIDC, Lung Image Database Consortium, which has a number of lung CT scans and the annotated lung nodules present in them. These lung nodules have a diameter ranging from 2 millimeter and going up till 69 millimeter. There is another data set that is used by the researchers, which is Luna 16. It is actually a subset of LIDC, and it has lesser number of CT scans and hence lesser number of nodules present in them, as the lung diameter range is limited to 3 millimeter and 33 millimeter. Now, we introduce Unitochest, which is a lung CT scan dataset. It has 20% more CT scans than LIDC and 25% more annotated lung nodules than LIDC. Furthermore, our dataset is not only larger in terms of CT scans and the annotated nodules, it is also more diverse in terms of the diameter and size of lung nodules that are present in them. The range of our nodule lies between 1 millimeter and it goes above 100 millimeter. Our dataset consists of lung CT scans in DICOM format. All of the metadata has been cleaned out. The sensitive patient information has been removed from the metadata file. Those CT scans that have a cancerous lung nodule present in them have their respective lung segmentation mask available in PNG. This dataset is publicly available and is ready to use for the researchers. The total number of patients that were used in our study is 623. As I have already told you that our dataset is not only larger, but it's more diverse in terms of the nodule size. Furthermore, we have captured this data from 10 different machines to remove any kind of biasness that could be introduced by using a specific type of equipment. Furthermore, we have tried to create a balance between both the genders, male and female, that were used in our study and the age group that they belong to. Now that we have covered the data set, let's talk a bit about the problem statement at hand. So now we need to segment and detect the lung nodules from the said data set. In a standard approach, first the detection of the lung nodules is done and then the segmentation is carried out. In our approach, we have done it the other way around. We have first segmented the said lung nodules and then moved on to the detection part. For the experiments, we have divided our dataset in 80, 10, and 10, 80% belonging to the train set, 10% to the validation set, and 10% to the test set. We have assigned one single split to each patient to remove any kind of overlapness that could be introduced between the images. Furthermore, we have tried to balance out these splits with respect to the demographics, and we have also divided our splits with respect to the lung diameter size, just to see whether the neural network works better on the smaller nodules or on the bigger nodules. For the pre-processing, we have used a window center of -500 and a window width of 1600. For those of you who are not familiar with how CT scan works, CT scans are measured in terms of Hounsfield units, which is actually a measure of radiographic density. It is used to distinguish between different surfaces. So we have used this specific range to capture the lung area, the air around it, and the soft tissue that surrounds it. For the segmentation part, we have used state-of-the-art unit that is available. We have used a unit that is built from scratch and trained on our network. And secondly, we have used a unit that is pre-trained on LIDC dataset and then on our dataset just to see if the pre-training does any kind of improvement. Coming towards the segmentation results, for the results, we have used intersection over union, dice loss, and binary cross entropy loss as the measure of performance. The unit that was built from scratch and trained on our dataset achieved a dice score of 69%, whereas the unit that was pre-trained on LIDC and then on our network achieved a dice score of 72%. So that gives us 3% improvement in the dice score. But this improvement was observed in the smaller nodules, in the nodules that had a smaller size, which makes sense because the LIDC has more of smaller nodules and we have a larger and more diverse nodule range. We have shown the results of our segmentation by overlapping the segmentation predicted by the network on the lung CT scans. Now coming towards the second part, that is the detection part, we have used the model that was used for the segmentation. And for the measure of performance, we have used specificity and sensitivity. When we used only the positive images in our training set, by positive images, I mean only the images that have a cancerous lung nodule present in them and thus have a lung segmentation mask, we achieved a specificity of 80%. And a sensitivity of 95%. To further remove the number of false positives, we introduced 10% of negative images in our training set. The negative images are those images which don't have any lung cancerous nodules present in them and thus don't have any segmentation mask. By doing this, we increased our specificity to 95%. For comparison with a baseline technique, we compared our methodology with a binary classifier based on ResNet 18 that was pre-trained on ImageNet. We did this and the ResNet 18 achieved a specificity of 82% and a sensitivity of 74%, which is lower than our methodology that does the segmentation part first and then the detection part. So in conclusion, we have introduced not only a novel data set that is larger and more diverse, we have also introduced a methodology to segment and detect the said lung nodules from this data set. Our data set is publicly available on the given link along with the code that we have used to achieve these results. So anyone can use it. This work has received funding from the European Union's Horizon 2020 Research and Innovation Program. Thank you so much for your time and attention. If you have any questions, let me know.
Okay. Thank you for your presentation. Any question for the speaker? I have one question for you. Okay, the basis of your work is to propose a novel data set according to my understanding of the problem, that would be characterized by images whose quality is better than state-of-the-art data sets, right? Mm-hmm. Okay. For this goal, which are the basic criteria, qualitative or quantitative, you followed to obtain such a data? Thank you.
Okay, so as I told you that, first of all, talking about the quantitative data, as big as the data set is fed into the system works better. So we have a larger data set. So in terms of quantitative data set, we have a larger data set. We have not put more focus on the qualitative part.
Okay, but I was meaning quantitative in the sense if not only the quantity of images, of course, the amount of images is important, especially in deep learning. But I mean, in deciding the design of the data set and the characteristic of images, there has been some quantitative measurement that allowed you to say, okay, this image, this data set on average is better than state-of-the-art one. Not only in terms, I have 10,000 images and the other ones are only. Please.
Yeah, okay. So we have covered the quantitative part. Talking about the qualitative part, we have introduced a data set that is more diverse. So the state-of-the-art data set that was already available has a lung nodule diameter ranging from 2 millimeter and going up till 69 millimeter, which is good, it's fine. But as we know that the cancer can spread, and if the neural network is focusing only on the nodules that are smaller in size, it may miss out the nodules that are bigger in size, and there might be false negatives in the predicted results. So we have introduced a data set that has a more diverse lung nodule range. So it can capture both the smaller nodules and the larger nodules. So the false negative rate could be lowered.
Okay, good answer. Just one last question for you. From my side, if other questions are present, I'm glad to leave the word to someone else. But this measurement you mentioned now, what about the distribution of this diameter? I think it is okay in a data set that the distribution is made uniform, or we should follow the prior probability of the diameter distribution, in your opinion?
We have not followed a uniform distribution. The distribution is mentioned. We have mentioned how many nodules we have, what is the range. We have made a graph and made it available in our paper. But we have achieved all of the data set that we could from the hospital and worked with and worked with what we could get best.
Thank you very much for your answers. Okay, this was the very last presentation. So even this last session closed with this one. So I invite Professor Distante to join us and to conclude.
Okay, I'd like to thank Gianluca for chairing the last session. Let's give an applause to him also. And here the end of the conference comes. This is the closing of this conference. Unfortunately, the latest competition has been dropped. So I would like to thank all of you for attending the last session, for attending the entire conference. It has been full of sessions and several events. It's been very, very long, five full days of events. A big thank to the technicians. Please give them an applause. They did a fantastic job. And I would like to ask a local organizer to come on stage here, please. Let's. So Pierluigi, Publication Chair, Marco Del Coco for the liaison with the communication, Paolo for the finance, Pierluigi for the workshops, Maria Grazia for the finance, Arturo for the web, Antonella for the communication project, Marco for the program chair, and Francesca, the social media manager, which has allows us to communicate all of the events, the interviews, and everything related to this conference. So thank you very much to all of you, and we'll see you in the next edition of the International Conference on Image Analysis and Processing. Thank you very much.